Last lecture, let's see. Last lecture we had said that we'll look at biasing of BJT amplifiers in a evolutionary manner here, and we said we'll start from the simplest biasing, which you see over here, the first one, and then we'll gradually progress to the biasing that is more common and better, which is over here. So let's recall the first circuit that was there. What was the problem with it? The simplest possible biasing, the problem was sensitive to VB, extremely sensitive to VB, and very sensitive to temperature, and sensitive to sensitive to VB and temperature. These were the two problems that this particular circuit had. And a very simple solution to that particular problem was you add an RB here. And when you add an RB here, then what happens is if you choose the drop across the base resistance here that you see, the drop across base resistance, if you keep it sufficiently large here, then what you can do is reduce the sensitivity to temperature. All right, so that was the circuit that we went to in order to solve the problem of sensitivity to temperature that was there here. Here the collector current is an exponential function of base voltage, here is an exponential function of temperature. Okay, temperature enters into exponential terms. And while here the current is not an exponential function of VB, but it's more a linear function of VB here. You know that base current will be this VB minus the voltage drop minus RB here, and collector current will also be proportional to VB rather than an exponential function of VB here. The problem with this particular circuit was that the signal that you see here, signal gets dropped across RB, and we want the signal here to get dropped primarily across the transistor, because it's the transistor which amplifies. Any signal which appears across the base emitter part here gets translated into a collector current which flows across RS and RC and RL and develops a voltage here. So we want the signal that you see here to be dropped across base emitter junction here, and the signal was dropping across RB. A large part of the signal was dropping across RB, and in one particular case we saw that the voltage gain was actually less than 1. The other problem with this particular circuit was we said that many times the voltage that you use for biasing, one terminal would be ground, and the signal also would be one terminal connected to ground, and therefore we cannot simply stack them. So to solve both of these problems, we arrived at this particular circuit here. Here we see that the signal does not see RB as it travels to the transistor here, so we avoid that particular part. And also note that we have decoupled the biasing voltage here and Vs here. Both terminals are ground and they're still connected in series here. Now when we look at this particular circuit, so let's start from here. So this was the circuit that we had, and if we using the methods that we have discussed earlier, we can write down the small signal model for the whole circuit, where we'll consider capacitors as shorts. We'll look at only frequencies where the impedance due to capacitors is negligible compared to other resistors in the circuit. So we'll consider it as a short. The base voltage, of course, in a small signal modeling of the circuit becomes a ground here. This becomes a ground here. And then we replace the transistor by hybrid pi, and it's very simple to show that the voltage gain is minus GM RC parallel R. Now if I expand GM, if I look at GM, so the maximum gain that you can get from this particular transistor, as you can see, is GM times RC. If your RL was much larger than RC, then the maximum gain that you will end up with GM times RC. And if I write down what GM is IC by VT. So what we see here is something which is very important that you should always keep at the back of your mind, that the voltage gain depends on this product ICRC. Okay, this drop is important. Is this drop DC drop, by the way? Note IC is the DC current, and RC of course is the resistor here. So the voltage drop here, the DC drop here, determines how large the gain is going to be, because the gain is, as you can see, GMRC is ICRC by VT, and load resistance you do not have any control. Whatever load resistance you're given, you'll accordingly connect it here. So the gain then depends on this drop. This drop you would like to keep as large as possible. Okay, the larger the drop is, the more the gain that you will end up in general. Okay, yep. Yes, we did improve the temperature sensitivity of this particular one. How? Okay, let's go back and look at from the first to the second, right? Look at the first term here. The first circuit that you see here, the collector current is exponential function of VBE. VBE is nothing but VB. And therefore, if we write the percentage change in current, delta IC by IC, is, here we have written delta VB, but delta VB can as well be, even if you keep VB constant, what will happen is VBE will change. Okay? So it's the same thing. What you see is any change in VB gets multiplied by VB by VT, which is a large factor here. Temperature has similar effect. Okay? So temperature, we see that there is a large change here, a large effect of temperature. The other circuit, if we look at this particular circuit, when we add a resistor here, of course, we are assuming that the resistor is relatively temperature independent. Okay, we are not taking into account temperature dependence of resistor, which to a first order approximation is okay because compared to the transistor is much less dependent. Okay, so if we take this one, delta IC by IC is over here minus delta VB by VB minus VBE. So we note that any change in delta VB or delta VBE is reduced by this factor here. So if we keep VB minus VBE, which is the drop here, IB, RB large, if we keep this drop, let's say 1 volt, we said temperature may result in a change of, let's say 100 millivolt here, and we keep this term 1 volt here, you see that percentage change in current goes down, which is not the same in the last circuit here. Last circuit this was getting multiplied by this factor, which is very large. Okay. So that was the whole motivation for going to an RB. You never, in general, what you do is you never bias a diode or a transistor where you see a diode here directly by connecting a voltage across that particular sense. Because the diode or a transistor from the base side is an exponential function of voltage. And you don't do that. Exponential is such a sensitive function, you don't apply it directly to the transistor here. You always apply it through a resistor, which reduces the sensitivity. Okay. All right, so let's come back to, so the point that I was emphasizing is that keep in mind this term here. This term is important. Okay. All right. Now, when we have a circuit like this, it makes sense that why unnecessarily use two supply voltages, one to bias from the collector side, one to bias from the base side. A more efficient circuit would be if you simply did this here. Simply use the same power supply here to bias from the collector side as well as from the base side as well. So instead of using the same VB here, why not do that? That's a more economical circuit. You don't need another supply voltage. Okay, so that's the motivation to go towards this particular circuit. All right. So it's similar. Of course, this offers you less freedom. Here, for example, VCC could be whatever supply voltage you wanted, and VB could also be something else. Now the fact that although it's simpler, but remember what you have done is that VB is equal to VCC, so it constrains your circuit. What you could do earlier, perhaps you can't do it here, because the voltage from this side and from this side is the same. So this comes at a price which you will see later on. Okay, the simplicity comes at a price, and the price is the loss of flexibility. And therefore, what happens is sometimes you may want to design it in such a way that you may want VB to be different as VCC, but you can't do that here. Anyway, that you will realize only when you try to design for different cases here. Okay, now if we look at this particular circuit, now the problem is that we have solved. As I said, if you keep the drop across RB, which means the drop across RB here, if you keep it sufficiently large, you get rid of the problem of sensitivity to temperature, sensitivity to base emitter voltage. Now, the other problem that this particular circuit has is, if we look at the circuit here, IB is nothing but VCC minus VB by RB here. If we look at this side here, that's IB. And IC is beta times IB. And therefore, if I examine the sensitivity of my circuit to beta, and we define sensitivity, percentage change in collector current divided by percentage change in beta, and straightforward IC is beta times IB, so you can easily see sensitivity is 100%. If beta doubles, the collector current also doubles. So that's, as I said, beta can vary significantly from one transistor to the other, and therefore that's a problem in my circuit. That the circuit is very sensitive to beta. So that's the problem that we have to address. Okay, so the issue is, how do we do that? And so what we do is, this is again a principle that is very, very important in analog circuits. We use the concept of negative feedback. The way we reduce the sensitivity to beta is that we employ negative feedback. And the way we are using negative feedback in our circuit is by putting a resistor in the emitter. Okay, that's what this resistor does. It adds negative feedback. So let's see how it does that. Okay, so this is the resistor here. And what it does is the following. You can see how negative feedback operates. Let's say you have biased the circuit. If beta increases, we know the effect of beta increases to increase collector current. All right, collector current increases. If collector current increases, this voltage VE that you see here will go up, because a larger current means a larger drop here. VE goes up. If this voltage goes up, base emitter voltage is relatively constant, doesn't change that much. So base voltage goes up. If base voltage goes up, what happens is VCC is fixed. So what happens is base current goes down. And base current goes down, which means it tries to counteract the earlier increase in IC. Okay, so you see that there is a feedback loop operating. All right. And once the feedback operates, negative feedback, which means that anything which tries to increase collector current, my feedback loop tries to counteract that and tries to reduce it. So obviously now I'm going to get lesser sensitivity to, let's say, any changes in beta, which we can see by writing down the equations here. Okay, so let's write down the equation and see. Let's start from here. Let's start from this side here. Let's write down the KVL. So KVL is VCC. The VCC equal to IB RB is this drop here. Then VBE here, the drop from the base emitter voltage, and IE RE, which is the second drop here. And base current, we can write it as IC by beta. IE, we can write it as beta plus 1 divided by beta into IC here, into RE. And, we can take this term as practically equal to 1. And therefore, one can rewrite this as IC equal to VCC minus VBE RB by beta plus RA. Okay. Now, if you recall earlier when we didn't have RE, which means what? Just go ahead and put RE equal to 0. Right? If you didn't have RE, so RE equal to 0. IC was VCC minus VB by RB by beta. IC was directly proportional to beta. So it was very sensitive to beta here. Now, what we have done is we've added an RE term here. So obviously now sensitivity to beta has reduced, because there's a second term here which doesn't depend on beta. Now, if I want to make it very insensitive to beta, what should I do? Make RE much larger than RB by beta. That's what I need to do here, right? So now if I take this expression and calculate sensitivity, delta IC by IC divided by delta beta by beta, it turns out to be equal to 1 by 1 plus RE by RB by beta. So it's a simple differential that you can do, and rearranging the terms, you get this here. So that's the sensitivity. And it shows if you want sensitivity to be small, then what you should do is make RE much, much larger than RB by beta. So that's the design criteria. If you want to make your circuit insensitive to beta, that's how you should choose your RE and RB. If this constraint is satisfied, then your circuit will be insensitive. And it all depends on how large you take. If you take a factor of 10, at least let's say a factor of 10, then of course you'll get sensitivity which is around 0.1 or 10%. If you want even better, then you'll have to take even larger. Okay, so this is the important criteria here in designing. RE here should be larger than RB by beta. Okay, so let's see what the consequences will be. Yeah. Do we have a? Yeah, I cannot choose any large value of RE. That's what you'll see. Whenever you do a design, you'll see that your requirement of bias instability will conflict with other requirements. There are always trade-offs. There are always, the resistor value that you put in here has implications. You can see, for example, let's say as we go forward, we'll see. Okay. All right. So if you do that, if you make RE much, much larger than RB by beta, what you are saying is then the first term is negligible. Then what you are approximating it as VCC minus VB by RE. That's what you're doing. Okay. So IC becomes that. Now, I'm sure if you look at this term, you can see already problems. Why? Taking RE much larger than RB by beta. If you do that, you get this one here. Okay. I don't know whether you see a problem already. What this implies. This is implying that the drop across this resistor is small. The drop across this resistor is small. Okay, it's only that. Let's go forward and see. Okay, so I have IC equal to VCC minus VB by RE. Let's do the KVL on the output loop. On the output loop, if I do, I get VCC equal to ICRC plus VCE here and plus ICRE here. So instead of IE, we have written it approximately as IC. Okay, so that's the loop on the output side here. And we can rearrange it and write it as IC equal to VCC minus VC by RC plus RE. Okay. Of course, who is going to decide the value of IC here is this equation. This equation will decide, because once you apply VCC and you choose RB and RE and all that, this equation decides what is IC. And this equation is not the one deciding IC. What happens is you calculate IC from here and then you put it over here. And what this does is it decides VCE. It's not the other way around. Don't, even though I've written it like this, doesn't mean that this is the controlling equation. This is not the controlling equation. The collector current is decided by the input side here. That decides my collector current, and then this collector current flows here, and VCE, I get a certain value of VCE depending on how much IC is set by this particular equation. Okay? Alright. Now the reason why I've written it is as follows. I've written deliberately IC as VCC minus VC by here, because now I want to equate these two terms. Okay? These two terms. And from there, what I can do is I can get a ratio of RC by RE. Okay, I have IC here given by this term, and I have IC here, VCC minus VC by RC plus RE here. I equate these two, and then, I get RC and RE an equation, and if I rearrange, I get RC by RE has to be equal to VB minus VCE and VCC minus VB. That's the equation that you end up with. So what it is saying is the following. If you make your circuit insensitive to beta, then you'll get an equation like this. And this, of course, is a simple KVL on the output side here. The implication of these two is that you will get RC by RE is VB minus VC, VCC minus VB. Alright, so why is that a problem? Problem is, if you look at this particular expression, okay, if you look at this particular expression, you note that VCE will be less than VBE. Everybody agrees? VCE has to be less than VBE because all my resistors are positive. These are physical resistors. Their values have to be, RC has to be greater than 0, RE has to be greater than 0, which implies that if you design it like this, try to make the circuit very insensitive to beta, then your VCE will be less than VBE. Which means what? Base emitter voltage is what? Around 0.7. Okay? And VCE then has to be less than VBE, which means maybe 0.5, maybe 0.4. Now, what is the problem with collector emitter voltage becoming 0.5 and 0.4? You've gone very close to saturation. Very close to saturation. You're at almost close to the edge of saturation. That's the problem. Okay? So that's one. The other one is, typically, if I look at it, RC will become less than RE. You can easily calculate. RC will become less than RE. Why? Let's say I have VCC equal to 5 volt. So I have 5 here. VB is 0.7. So I have 4.3 here. And this is, let's say, 0.7 minus 0.5. I have 0.2 here. You can see RC is less than RE. So you'll end up, no matter how you design, if you try to make the circuit insensitive to beta, you find that your collector emitter voltage becomes very small. You get close to the saturation region. And we'll see later on that as you get close to the saturation region, you can't get enough swing, voltage swing. Okay, so that's a problem occurred. The second one is RC becomes less than RE. Now, what happens if RC is less than RE? So this is the problem that I was saying. Your bias point is getting very close to saturation. Okay, so that's not a good thing because this is the bias point. And what happens is, note that as you apply a signal, this point will move here and here, and it will move as you apply the input signal here. And what happens is, it's already very close here, and the transistor will very quickly enter into saturation. And once it enters into saturation, you start getting distortion. So that's the problem. First problem that I'm saying, VCE is less than VB is not a good feature here. The second one is, we said RC by RE is here, and RC becomes less than RE. Now what happens is, if I took this circuit, now I'm not reproducing all those small signal analysis again and again. If I took this circuit and I calculate voltage gain, which is V0 by Vs here, I will get GM by 1 plus GMRE multiplied by RC parallel RL. This is what I will end up with. Okay. Now, if I look at this particular expression, the first term, if I look at it, GMRE, what I can show from here is that this one is going to be less than RC by RL. Okay, RC parallel RL is obviously less than RC here, and this one, GM by 1 plus GMRE, if I neglect 1 here, then I get 1 by RE. So obviously then this whole term gain will be less than RC by RE from here. So what do I see? That RC is less than RE and my voltage gain is RC by RE. So what it tells is you can't get any voltage gain from this circuit. If you design this circuit in this particular manner, you cannot get any voltage gain. Alright. So what we did was we put in RE here, and we said, why did we put in RE? We were trying to put in negative feedback. And we said that if you put in RE, you can make the current insensitive to beta through negative feedback. But if I do that, then this is what I end up with. I get RC less than RE, and therefore I get a gain which is less than 1. And, my transistor is biased very close to saturation. So I end up in all these problems. Okay? Yes. There are two reasons. We'll see. You're right. The gain does depend on IC, RC, but that was for a circuit where this point was ground. That was, earlier we had a circuit where this point was ground, and then we didn't have the first term. We simply had GM, RC parallel RL. And therefore the most important term was this drop here. Now what we have is, when we put in RE here, we get this additional 1 plus GM RE here. So now realize what the problem is. Please keep this point, which is very important, is the signal is coming in from here. Okay? The signal is coming in from here. What amplifies is the fact that the signal, part of the signal which appears across base emitter voltage. Whatever appears across base emitter voltage here, if you go back and look at your hybrid pi model here, whatever appears across base emitter voltage, that gives rise to a current which is GM times VBE. And that current then flows through RC to develop the voltage here. So the most important thing is, whatever voltage you apply from here, you want it to appear across only the base emitter. Now what happens? The voltage that you apply from here gets dropped across base emitter, gets dropped across RE also. Gets dropped across RE also. Whatever voltage you apply here, you can see it will go here. The voltage that you apply from here will be between this point and ground. And therefore it will appear across the base emitter and across RE. So our problem is, this term that is coming about is mainly because my part of the signal is dropping across RE. Okay? So is that suggesting a solution? Why do I need an RE? I need an RE to put in negative feedback for biasing. Biasing is what? DC. And my signal, if I'm saying, is sinusoidal, I don't want my signal to appear across RE. What does it suggest? Just bypass the RE by a capacitor. Just take RE and bypass, because I don't need RE for my small signal circuit. I need RE only for biasing. So what it suggests is that if I bypass this here by a capacitor here, then this term that you see here will go away. Because once I bypass, then this term will become a small signal ground, and then I recover back my original circuit here. Okay? So this is just an example of the fact that I get very little gain. So the idea is then that we take this particular circuit, we don't want our signal to appear, get dropped across RE, because that's a waste of my signal. I want it to appear across base emitter voltage here. So we put in a capacitor here. When we put in a capacitor here, now I get gain, which is GM RC parallel RL. I don't get this term now. RE doesn't appear because RE is shorted by a capacitor, doesn't appear into my analysis. Gain becomes GM RC parallel RL. Okay? Alright? Now, the problem is not solved as yet. Let's look at it here. Okay? The problem is not solved. It's only partially solved. So, we have put a capacitor here. And so, gain now is GM RC parallel RL. The magnitude of the gain will obviously be less than GM RC. If RL is, let's say, very large. And GM we know is ICRC by VT. So, we've said that the ICRC drop is important for us. Okay? Alright. We've also said that if I want my circuit to be insensitive to beta, I should choose my second term to be much smaller than the first term to be much smaller than the second term. So I should make it VCC minus VB by RE. Alright? Okay. And we have this IC equal to VCC minus VC by this one here. Okay. So if I take some values here, say, if I look at my ICRC here from both of these equations, we have shown that ICRC is less than or equal to VB minus VCE here. And that VB minus VCE, VB is about 0.7 and VC can be at the most, if you get very, very close to saturation region, VC can be at the most 0.2. And therefore, this term ICRC has to be less than or equal to 0.5, which means that your gain has to be less than 19. And that too, you are very close to saturation. You are at the edge of saturation. So if you bias it at the edge of saturation region, which means that the transistor is not very useful. Okay, little bit of swing here and the transistor will go into saturation, the signal will get distorted. Even then, if you do that, all that you get is a gain of 19. Okay, so it's a very moderate amount of gain, and that too by getting very close to saturation here. This constraint is simply coming from these two. Okay, ICRC is less than or equal to VB minus VC, which is less than 0.5. So that's the problem with my circuit. I have to push it really close to, even by connecting CE, I have to push it really close to saturation to get a reasonable amount of gain. So that's not something which is very useful. Okay, let me put this point in more detail here. Now, note the following. You'll see the same thing in a different way. If I say IC equal to VCC minus VB by RE, right? If I neglect this particular term and say this term is smaller than RE, what I'm effectively saying is that this term is practically equal to VCC. Look at this equation here. If you look at this equation, what does it tell us? It tells us that this term is almost equal to VCC. The drop is negligible. This is VCC. If this is VCC, what is the voltage here? VCC minus VBE. And so this voltage becomes VCC minus VBE divided by RE gives me what? Collector current or emitter current, which is the same. So when I write it like this equation, effectively what it is saying is this node is at VCC here. This node is at VCC minus, let's say, 0.7. That's what it is telling us. Okay? When I write it in this manner. So as you are trying to make your circuit insensitive to beta, you are saying this term is much smaller than this one. And therefore you're getting here, which is effectively saying that this voltage is VCC. You're saying that the drop here is negligible. Okay? You're saying the drop here is negligible. Which means what? If this point is VCC minus 0.7, then the drop from here to here will be only 0.7. If this term is VCC minus 0.7, then the drop, this is VCC here, and this is VCC minus 0.7 here. So the drop from here to here will be only 0.7. So it tells you now, you have the drop from here to here is going to be 0.7. What can you do? If you just force your transistor to the edge of saturation, you'll make it 0.2. And only thing that you get RC is 0.5. And I told you, for gain, what do you need? ICRC drop to be large. You require large ICRC drop here. This drop, the drop across ICRC, this drop you want it to be large. And we are saying, from here to here, I have only 0.7. Okay? I have only 0.7. And therefore, this is not going to work for me. This circuit is not going to work for me because I have only 0.7 here. So now the issue is, what do we do? Well, I could, for example, increase, say, suppose, so here, just keep this in this mind. Let's say this is 5. If this is 5, this is 5 here, this is 4.3. Okay, 4.3, and therefore I get a drop of 0.7. But suppose I increase the drop across RB and I make it 4. If I make it 4, this will become 3.3, and the drop from here to here become 1.7. Now I have a sizable drop, and I can get gain, and I can bias it also. But then if this becomes 4, what happens? There's a drop across the base resistance of 1 volt. And the drop is due to what? Because of IB. And IB is what? Then the beta comes into picture. Because the relationship between IC and IB is through beta. Beta comes into picture here. So I won't get this term then. What will happen is RB by beta will become significant. And my circuit will become sensitive to beta. So I'm ending up in a problem now. If I try to make it independent of beta, I would like to make it VCC here. And then I don't get any gain or swing. On the other hand, if I make this larger here, then my circuit becomes sensitive to beta. So now the issue is, how do I overcome this conflict? All right. So you can see obviously I want to increase this. If I want to increase this, you'll see the solution from here itself. The problem carries within it the seed of solution also, if you understand the problem properly. So we want this to increase, obviously. We want it to increase, which means suppose I want it to be, as I said, 1.7. I want this to become 4. I want this to become 4 volt. But I don't want it to become 4 volt due to base voltage drop, base current. Because base current that flows in makes my circuit beta dependent. But I still want it to become 4. I want this voltage, note what I'm saying is, this is 5, I want this to become 4. But not due to base current. Because any base current brings in a beta. How do I do that? How do I make it 4, but not due to base current, due to some other current? Now, if due to some other current, where will that current flow? If it's not the base current which is adding to this extra drop, I have to add something else which will cause that drop. Okay, so that's what I'll do here. Okay. So the idea is, how do we reduce VB here? How do we reduce VB without making it base current and thus current gain dependent? Which means I want this voltage to drop, but not due to base current. So what I do is, I want more current to flow. So some extra current to flow. Because I don't want the drop to increase because of IB. I want a separate current I to flow here to increase, to make this voltage lower. Now, if this is I here, IB of course flows in, then I have to provide a path for this I here. Okay, and so that's what I do. I add a resistor. So now you see this, why I'm adding this particular resistor here, R2. I'm providing a path now for an additional current to flow from R1 and going down to R2. And what this will do is, this current I will now cause this voltage to drop. And as this voltage drops, this one drops here and I'll get a larger voltage drop here. And therefore, I'll be able to get swing. Here, I will be able to get sufficient collector emitter voltage and also the drop here. So that's the motivation for adding this R2 here. Otherwise, I was getting into a conflict that if the only way I could reduce this VB is by making the drop larger, and the drop was due to IB, and the whole thing was becoming beta dependent. Okay, so we arrive at this particular one, R1, R2. So then, this is our circuit then. We have arrived at a final circuit where we have this transistor, we have RC, R1, R2, RE, and all of that you see. Okay, this is our final circuit, and we realize what the role of each particular element is, right? What is the role of RE? Negative feedback to reduce the sensitivity to beta. What is the role of CE? We don't want signal to drop across the RE. We want signal to appear only across this one. So that's why we put a bypass capacitor CE here. This, of course, CC is there. I don't want my biasing to be affected by my load here. So that is there. And R2 we have seen. We put in R2 because we want this voltage to be lower. This voltage we want to pull it low in order to get enough gain without making the circuit sensitive to beta. So that's the circuit that we have, and of course we apply the signal from this side. Okay. So now what we have to do is we have to take this particular circuit and now do develop a set of equations which will tell us how the biasing is done. Okay. So what we are doing is we are doing the bias point analysis here. So we have RC, RE, R1, R2. And what I want to do is derive expressions for collector current and all that here. So the first thing that I do is I separate it out. Okay, it's the same circuit, redrawn. This is VCC here, this is VCC here. If I redraw like this, then what I do is this part that you see here enclosed, I apply Thevenin's equivalent to it. Thevenin's equivalent where? Between this point and this point here. Between here and ground. So if I apply Thevenin's equivalent, the open circuit voltage is going to be simply a voltage divider. Open circuit, if I cut it here and I ask what is the open circuit voltage, that's going to be R2 by R1 plus R2 multiplied by VCC. What is the Thevenin's resistance looking from here? R1 parallel R2. Remember what this will become? Thevenin's resistance, this will become ground. Okay, so that's what we do here. This circuit that you see transforms here. You get some voltage here. This is my Thevenin's voltage, VBB, and this is my Thevenin's resistance here. So the voltage is, Thevenin's is VCC R2 by R1 plus R2 here, and Thevenin's resistance is RB R1 parallel R2 here. So I get this circuit, okay, from the original one. And once I get this circuit here, I write down a equation in the base loop here, input loop, VBB equal to IB RB plus base emitter voltage plus IC RE here. That's the first equation here. And I know the relationship between IC and IB. So I get IB is IC by beta. So I get an equation IC equal to VBB minus VB RB by beta plus R. So that's how my collector current is decided through this one here. I know how to calculate VBB here, RB, everything is known. Of course, to make the circuit insensitive to beta, I'll have to do my design in such a way that RB by beta is much smaller than RB. Which effectively means what? That the drop here across this one is negligible. Okay? Making RB by beta much smaller than RE is same thing as saying the drop across this particular resistor is negligible. Because you can see here, the IC will then turn out to be VB minus VB by RE, which is same as VBB up here goes over here. VBB minus VB is here, divided by RE gives us the collector current. Okay. This we have seen, sensitivity is RE. So when you take that particular circuit, one of the design criteria is RE should be much, much larger than RB by beta. That is what will make the circuit insensitive to this thing here. Sensitive to beta. Alright, so that is there. And so sometimes, if the circuit is designed properly, designed in the sense, if it is designed in this particular manner, RE much, much larger than RB by beta, what we are saying is VBB appears over here. So you don't have to go through this complicated analysis. All that you do is, this is VCC here, the voltage drop is VCC R2 by R1 plus R2. So this is the voltage that appears here. And then you say the voltage here is this voltage here minus VBE, and the whole thing divided by RE gives you the collector current. So very quickly, if you want to analyze, all that you do is find out, assume it to be a voltage divider, find out this voltage here, and then you know this voltage here, and this divided by RE will give you. That will give you the right answer only if the circuit is designed to obey this equation. If the circuit is not designed to obey this equation, then this method will be wrong. Because then it means there's a drop across RB here. Okay? So you can check, given an RE and given R1, R2, you can check if RE is at least 10 times larger than my RB by beta or not. If it is, then you can do the simplified analysis. Otherwise, you have to go to more elaborate here. So let's look at this one. A concrete example here. So we are given 10K, 10K, 4K here, 5.3K here. RB, the first thing that you do in calculating the bias point, you calculate RB, R1 parallel R2, for us is 5K. We check RB by beta is 0.05, 5 divided by 100, 0.05, and RE is 5.3K. So this is satisfied. So what we can do is we can simply calculate VB here, voltage, which is equal voltage divider here. So we get 6 volt. The emitter voltage then becomes 6 minus 0.7 straight 5.3, and 5.3 divided by 5.3 gives me approximately the collector current. And once I get the collector current, then I can write a equation in the output loop here, VCC minus ICRC. So I get 8 volt here, and VE we know is 5.3 emitter current multiplied by this here. So we get VCEQ, which is 2.7. Okay. So analysis is very simple. But note, you have to check this, if this is true. Similarly, suppose I have another circuit like this. Now note, RB is 100K, parallel 100K is 50K. RB by beta is 0.5K. And this is 2K here. Obviously, it's not negligible. It's not negligible. But suppose you're not careful. You don't look at this one. And you say, well, this is 12. So you will say this is 6 voltage divider. And if you go ahead and do the same thing here, 6 here, what you would end up getting is 2.65 milliamperes. So if you simply take 6 minus 0.7 divided by 2K, you will end up getting 2.65 milliamperes. Actual current is 2.12 milliamperes. So in this case, RB by beta is not negligible. That's why I said, if RB by beta is negligible compared to RE, then you have a simplified analysis. Otherwise, you have to go to this equation, which means that this is not a properly designed circuit in some sense. This circuit will be sensitive to beta. Okay. All right. So that's the biasing part here. The small signal part, let's see if it makes sense. The small signal part, remember what will happen is, we're looking at the mid frequency where all the capacitors are short. This is a short, this is a short, this is a short here. The VCC will become ground here, and therefore I will get a circuit like this here. When it becomes a short, I will get R1 in parallel with R2. So that's called RB. The transistor, of course, has been replaced by its hybrid pi model here. RC will come between this node and ground. So that's RC here. And RL is also between this node and ground. So you end up here. And the gain is now straightforward. GM times R0 parallel RC parallel RL. And GMRC is ICRC by dt here. Okay. Okay. So that's the gain of the circuit. So we have an amplifier now available to us. We know how to bias it, and we know how to calculate its gain. AV will turn out to be GMRC parallel RL. Okay. So before we stop, I'll take up this design example here. So previously, what I was giving you is, I was giving you R1, R2, RC, RE, all of that, and telling you to find out the bias point and let's say the gain. Now, suppose I have a circuit is given to me, and I say I want to design for 1 milliampere and 2.5 volt here. Okay, and supply voltage is given as 5 volt. How do I start? Where do I start? These are my equations. All the equations are given to you. VBB here is VCC R2 by R1 plus R2. IC is here, RB is all that here. So how do I start? Well, these are the equations, but remember the constraint is what? RB by beta is much, much less than RE. I must design it in such a way that this is true. Okay? The other one is, I must choose VBB much larger than VBE. Where is this coming from? Where is this coming from? This coming from a past discussion. If you recall, if you make RB by beta much smaller than RE, what happens? This term goes away. My circuit is insensitive to beta. But now it's insensitive to beta, but IC is equal to VBB minus VBE by RE. What can cause a change in IC now? Temperature. What will temperature do? Change VBE. Remember, for every 1 degree rise in temperature, my VBE goes by 2 millivolt. So how do I make my IC insensitive to temperature? I make VBB much larger than VBE. You know, if that is true, any change in VBE is not going to do that much change to my collector current. Right? So that's the constraint that is coming from here. I want my biasing to be temperature independent. That's why I must keep a sufficient gap between VBE and VBE. VBE must be much larger than VBE. Now, the larger you make, the more insensitive it will be to temperature. Similarly, the larger you make this one, the more insensitive it will be to beta. Now, you have to decide how much larger can you really make. Both of these things you have to balance. Now, in some design, if somebody tells you that your circuit is going to work only at room temperature, it's going to be inside the room, air-conditioned room, and the temperature is not going to change. well, then maybe this is not too important for you, right? So you can choose VBB close to VB. It will not matter that much. And maybe that is more important. So it all depends on which one is more important and which one is less. But let's say we have both of these constraints to keep in mind. And so if you look at these equations here, then there are many possibilities of choosing R1, R2, RC, RE and all that. There are many possibilities. But we have to choose them keeping in mind that I want my circuit to be insensitive to beta and I want my circuit to be insensitive to temperature. So these are the two constraints. And they are the ones who will decide how you go ahead with your design. So the first thing is, one key choice is VBB. You have to start with a choice of VBB. How large do you want to make VBB? You have to start with that. If you don't start with a choice, as I said, the equations are not enough to determine a unique value of RC, RE, R1 and R2. They are not, if you have three variables and you have three equations, then there's a unique design. We don't have that. The number of equations is less and the number of variables are large. Okay. So, which means then I have a choice available to me, how I design it. And how do I decide? These are the choices that are there, as I said, key choices. What value of VBB do you choose? You want it to be larger than VBE here. So, let's say I choose. Now, that's where, as I said, it's a little bit arbitrary. And it's arbitrary because I don't know how much importance to give to this particular thing. If I had an application in mind where I knew the temperature is going to change so much and the requirement was that my biasing should not change and all of that details, then this would not have been arbitrary. From those requirements, I would have derived how much VBB do I need. Here, all that I've done is I've chosen VBB larger than VBE, not too much larger, 1.7, 1 volt extra that I've chosen. Okay. So this is arbitrary, but remember the implications of that. Okay. So 1.7. So once I choose VBB equal to 1.7 here, note, I'm also going to make my circuit insensitive to beta. So if this is 1.7, then my VE becomes 1 volt, 1 volt here. And if this is 1 volt and ICQ is given as 1 milliampere, it means I immediately know RE. So note the implication. The moment you choose VBB, it immediately decides the value of RE. VBB, the choice of VBB decides the value of RE, straight. Okay. And once I choose RE, note, if I choose RE, I know the drop here. I know the drop here, and I know the drop VCEQ is given to me. So what gets decided? ICRC. The collector voltage gets decided. ICRC drop gets decided here. And since I know IC, it immediately decides the value of RC. So note the implications here. Your choice of VBB here immediately decides what is RE and RC. Straight. RC and RE get fixed. Okay. The choice of VBB here. Yes. These two. You have to keep in mind, this is what you are looking for. 1 milliampere and 2.5 volt. And you have to obey these constraints. Both of them. Both of these constraints you have to keep in mind. Your VBB here should be larger than VBE here, sufficiently large, and RB by beta should be sufficiently small compared to RE. These are the two things that you have to keep in mind. And as I said, one way of attacking the problem is making a choice of VBB here, deciding a VBB. Once you do that, immediately your RE gets decided, your RC gets decided. Okay? Alright, let's go forward. The second choice is RB. Note, the second constraint is RB by beta is much smaller than RE. Now, the issue is how much smaller do you want to keep? Because once I know RE and I know beta is nominal value is 100, so it says RB should be much smaller than 100K. That's the second choice. How much smaller do you want? 1/10, 100, or what? And there'll be consequences of your choice. Okay. So now here I'm saying I'm choosing RB to be 1/10 of this value here. Much smaller for me means 1/10. So I make it 10K. And now expect 10% error. Why? Note here, this RB by beta is 1/10 of RE. So which means it's 0.1. Okay, so in that sense I'm saying it's 0.1 times as compared to this one. So any change here will then result in the change in IC. Okay. Alright, so I get here and I know VBB already, VCC R2 by R1 plus R2, I've made this choice here. This is approximate, so don't take it too seriously here, 10% here. Okay, all that it's saying is a circuit will be to some extent sensitive to beta. So I have these two equations now, and straight away I get R2 and I get R1. My circuit gets designed. R1 and R2 both get designed. Okay, so the choices, as I said, are two. One way of looking upon it is two choices. That's it. Choose a value of VBB that you think is sufficient for your purpose and make a choice here. And then your values automatically get decided. R1, R2 and all. Okay. Now this is one way of going about it. Now it may happen that we'll see that input resistance when we look at the circuit depends on R1 and R2. That will put additional constraint on what RB I should put. Okay, there'll be other things. For example, constraint on RC will come from the fact that the gain is also dependent on that. Okay, so right now it's kind of a simplified design problem where all that we have said is ICQ equal to 1 milliamperes, VCQ equal to 2.5 with this designer biasing. Okay, and now we keeping in constraints in mind, and we said the choices are VBB here and RB much smaller than RE. If you make these two choices, your the biasing gets designed. Okay, so let's stop here. And all right, so that's the end of our discussion related to biasing here. We started with this one, then we went here, and we went here, here, and finally here. Right? Okay, so let's stop here.